When you hear the word explosion, what's the first image that snaps into your mind? Is it just one big chaotic bang, or do you maybe start to picture something more nuanced, perhaps even, I don't know, a controlled burst of power? Today, we're going on a deep dive precisely into that. We're unpacking the complex, often surprising, and frequently misunderstood world of explosions and explosives. Our mission today is, well, we've got a stack of compelling sources here. We want to extract the crucial insights, give you a real shortcut to being truly well-informed about this topic. We're aiming to understand not just what happens when something goes boom, but how and why it happens. Maybe most importantly, how we can actually control that immense power.
That's exactly right. Our source material today offers a really comprehensive look. We'll cover the various types of explosions, their associated hazards, and the critical control measures, the ways used to prevent them or at least mitigate their effects. We'll also get some deep insights into commercial explosives and, yeah, the truly insidious danger of dust explosions. This deep dive should give you a thorough overview and hopefully some real aha moments along the way.
Okay, great. So let's jump straight in then. Most people probably think of an explosion as just one thing, right? A sudden blast. But that sounds a bit like saying all cars are the same just because they have wheels. Our sources suggest there are fundamentally different kinds of booms, each with its own terrifying personality, maybe. Are all explosions really the same rapid expansion of gas?
That's a perceptive way to frame it, actually. And the simple answer is, well, no, a resounding no. Fundamentally, yeah, an explosion is defined as a rapid increase of pressure in a confined space, followed by a sudden release. But it's the speed at which that pressure builds and releases that really differentiates the major types. We mainly distinguish between deflagration and detonation.
Deflagration, okay.
Right. Deflagration is an exothermic reaction, meaning it releases heat that spreads slower than the speed of sound. It moves through mechanisms like conduction, heat moving directly through the material, and convection, where hot gases carry the heat, plus radiation, like the heat you feel from a fire.
Slower than sound. Okay, so what's the other one? Detonation?
Exactly, detonation. It's also exothermic, releases heat, but it's characterized by a shock wave. A shock wave moving through the material faster than the speed of sound.
Whoa.
Think of it as a supersonic event. It's essentially a physical shock wave traveling right through the substance itself.
So the core difference is literally the speed of sound. That fundamental speed gap, it sounds like it changes everything about how the event unfolds and its destructive power.
It absolutely does, yeah. That speed dictates the entire energy transfer.
So detonation is always worse?
Right.
Or can a deflagration still be catastrophic?
Well, detonations are generally far more destructive, per unit of material because of that supersonic shockwave. But a large enough deflagration, especially if it's in an enclosed space, so yeah, it can certainly still be catastrophic. Scale and confinement play huge roles.
Makes sense. Are there other types besides those two?
Yeah, our sources highlight some other significant categories. There's the boiling liquid expanding vapor explosion, or BLE. It's quite a mouthful.
BLEV.
Yeah.
This happens when a container holding a liquid that's way above its normal boiling point suddenly ruptures. The pressure drops instantly, causing the liquid to rapidly flash into vapor. And what's really dangerous is if that material is flammable. Well, you can get a massive, terrifying fireball.
Heights.
Then we have combustion explosions of dusts. We touched on this. That's the rapid burning of fine combustible particles when they're dispersed in the air and ignited. It's a very specific, often overlooked industrial hazard. We'll definitely circle back to that one.
Okay, good.
And finally, there's something called an unconfined vapor cloud explosion, UVCE. This is where a cloud of flammable vapor just out in the open air gets ignited. The flame accelerates rapidly enough to create a dangerous blast wave, even without being inside a building.
That's quite an array. From a relatively, quote, slow burn to a supersonic shockwave
Yeah.
and exploding clouds.
Right.
But okay, once that initial boom happens,
Yeah.
what does it actually do? How does something so fleeting cause such widespread destruction? What are the mechanics of the damage?
Right. The damage and injury from explosions primarily come from what we often call the triple threat. First, there's the blast wave. This is a pressure wave radiating out from the explosion. It causes damage through overpressure.
Overpressure.
Yeah, and here's where it gets really interesting, thinking about real-world impact. To give you a kind of shocking visual, even a seemingly low overpressure, like 1.0 psi, that's enough to knock an adult person right off their feet.
Just 1 psi? Wow.
Yeah. It's roughly the force of a strong punch, but spread over your entire body. Now, hit 5 psi,
Yeah.
and you're looking at enough pressure to snap a utility pole like a twig.
Good grief.
It just shows how quickly that invisible wave becomes this catastrophic force.
Okay, that's the blast wave. What's number 2?
Second are the thermal effects. If it's a combustion explosion, you get a fireball, right? Well, that fireball radiates intense heat. This heat can cause severe burns, sometimes 3rd degree. And it can easily ignite other materials nearby, which just adds to the devastation.
Right, spreading the fire. And the third threat.
And third, flying fragments. The explosion itself creates projectiles. Things like pieces of metal from whatever contained the explosion, glass from windows, wood from structures. These can cause significant damage and injury as they fly through the air at really high speeds. Shrapnel, essentially.
So it's the combination, isn't it? The crushing blast, the searing heat, and the shrapnel, they all combine in unpredictable ways, which makes explosions so devastating.
Exactly. That combination is what makes them so dangerous.
You mentioned dust explosions earlier, and you said we'd come back to it. I know our sources spend some time here. It feels different, because unlike a bomb or maybe a Beale Eve, these seem to just sneak up on industries. Can we really dig into why this seemingly, innocuous dust is such a potent, overlooked hazard?
Absolutely. It's a critical area, and you're right, it's often quite counterintuitive. Dust explosions happen when combustible dusts, and these can be organic like flour or wood dust, certain metals like aluminum powder, even some inorganic substances.
So lots of materials.
Lots of materials, yeah. When they're suspended in air within a certain flammable concentration and then ignited. But the mechanism is what's truly insidious. These often happen in a sequence.
It's a sequence.
Yeah. You might have a small initial primary explosion, maybe just a localized puff of flame somewhere in a plant, but that small blast disturbs accumulated dust that settled on surfaces, rafters, equipment, floors.
Right. Kicks it up into the air.
Exactly. Lifts it into the air, creating the perfect fuel-air mixture for a much larger, much more destructive secondary explosion. And this raises a really important, almost chilling question. Why is prevention so absolutely critical for what seem like tiny dust incidents, like that minor puff?
Because it's the trigger.
Precisely. Because that small puff isn't just a minor annoyance. It's often the trigger for something exponentially worse, a chain reaction that can devastate an entire facility.
That makes sense. How do we know how dangerous a particular dust is?
Well, the relative hazard is classified using 3 indices. These come from rigorous lab tests, usually compared against the standard, like coal dust. First, there's ignition sensitivity. Pretty straightforward.
Yeah.
How easily does the dust ignite?
Okay.
Then explosion severity. This measures 2 things. The maximum pressure the explosion generates and how fast that pressure rises.
The rate of rise, okay.
Right. And finally, the explosibility index. This is simply the product of the first 2 sensitivity times severity, and it categorizes the overall hazard, usually as weak, moderate, strong, or severe. This lets industries quantify their risk quite precisely.
Got it. So given how insidious these dust explosions can be and how devastating any explosion's triple threat is, what are the foundational steps? How do experts even begin to control this chaos, prevent these powerful events, or at least, reduce their severity?
The control strategies are definitely layered. You need multiple approaches. It's crucial for safety. One fundamental step is simply limit quantities.
Less fuel.
Exactly. Minimize the amount of explosive or flammable material you have stored in any one place. Reduce the potential fuel for a big event. Another is to prevent combustible concentrations. This means using good ventilation, good process design, to make sure that fuel-air mixtures are always kept outside their flammable range. If you don't have the right concentration, it just can't ignite or can't sustain an explosion.
Keep it too lean or too rich.
Precisely. Then, crucially, eliminate ignition sources. This is huge. It includes things like using intrinsically safe electrical equipment.
What does intrinsically safe mean exactly?
It means the equipment is designed to operate with such low electrical or thermal energy that it simply cannot generate a spark or heat hot enough to ignite a flammable atmosphere, even under fault conditions. It also includes grounding systems to prevent static electricity, build up a common culprit, and implementing really strict hot work permit systems for things like welding or grinding that obviously create heat or sparks.
Right, managing the obvious sources.
Yeah. And in some specific industrial processes, you can also reduce oxygen. You basically replace the air or dilute it significantly with an inert gas like nitrogen or carbon dioxide. No oxygen, no fire, no explosion.
Makes sense. What about if something does ignite? Can you manage the pressure?
Yes, that's a key mitigation strategy, especially for deflagrations. It's called provide overpressure relief. often just called venting. You design buildings or vessels with specific weak points, vents, rupture discs, blowout panels. These are designed to fail safely at a predetermined pressure, releasing the building pressure from a deflagration before it gets high enough to cause catastrophic failure of the whole structure.
So controlled release instead of an uncontrolled disaster.
Exactly. It directs the blast safely away. And finally, a really basic but effective one. Use distance and barriers. Separate quantities of explosive materials by significant distances. And use robust barricades, think reinforced concrete walls or earthen mounds, to absorb or deflect the energy from a potential blast wave, protecting people and other critical assets.
It really sounds like a strategic combination, doesn't it? Engineer controls, procedures, planning, all layered together. It's clearly not just one single fix.
Not at all. Robust safety relies on multiple independent layers of protection.
Okay, let's shift gears slightly. Let's talk about commercial explosives. These aren't just accidental hazards we're trying to prevent, like dust. These are incredibly powerful materials designed to explode for specific purposes.
Precisely. Explosives in this context are chemical compounds or mixtures specifically designed to create a rapid, self-propagating explosion. They're used for controlled applications like mining, construction, demolition, even defense applications. And because they're designed to be powerful, the Department of Transportation, the DOT, classifies them very meticulously to manage the inherent risks.
How are they classified?
Primarily into three main classes, A, B, and C. Class A explosives have what's called a detonating hazard. These are the high explosives. Think dynamite, TNT, blasting caps. They're designed to detonate.
The really powerful ones.
Generally, yes. Class B explosives function by rapid combustion, more like a very fast fire rather than detonation. Examples include some propellants, like for rockets or certain types of large fireworks.
So more of a push than a shatter.
That's a decent analogy for some applications, yeah. And Class C explosives are basically manufactured articles that contain restricted quantities of either Class A or Class B explosives. Things like smaller consumer fireworks or safety fuses. They still contain explosive material, but in limited amounts and specific configuration.
Okay, so these are incredibly powerful, intentionally explosive materials engineered for specific jobs. What are the rigorous controls needed? How do you handle them safely and make sure they only do what they're supposed to do?
The controls have to be exceptionally rigorous, as you say, because the power involved is immense and the potential for things going wrong is, well, severe. First and foremost is training and licensing. This is absolutely critical. Only properly trained, certified, licensed, and highly experienced personnel should ever handle explosives, period.
Makes sense. What about storing them?
For storage, explosives must be kept in specially designed magazines. These aren't just sheds. They're essentially fortified, often blast-resistant, secure storage facilities, designed to contain an accidental initiation and prevent theft. And here's a crucial detail, something that's often misunderstood outside the industry. Detonators and blasting caps.
The things used to set off the main charge.
Exactly. They must always be stored separately from other explosives, in their own magazine or a separate approved compartment.
Why is that separation so vital?
To prevent accidental initiation of the main stockpile. Detonators are sensitive. If one went off near a large quantity of dynamite, for example, the result could be catastrophic. Separating them breaks that potential chain.
That's a critical safety layer. Anything else on storage?
Yes, finally, there are quantity distance tables. And what's truly fascinating here, maybe even counterintuitive for some, is just how precisely engineered and regulated this is. We're not talking about rough guesses or rules of thumb. No. The American Table of Distances for Storage of Explosives, for instance, is a legal standard. It dictates, often down to the foot, how far apart explosive storage magazines need to be from each other, and also how far they must be from inhabited buildings, public railways, highways, based on the exact type and quantity of explosives being stored.
Wow, down to the foot.
It's a testament to how seriously this power is managed. It's complex physics and risk assessment turned into strict regulations to ensure public safety. It's really quite something when you look into it.
Wow, we've really covered a huge amount in this deep dive, haven't we? From understanding that fundamental difference between a subsonic deflagration and a supersonic detonation, to detailing that devastating triple threat, the blast waves, thermal effects, flying fragments, all the way through the sophisticated, multi-layered control measures that, aim to keep us safe. Understanding these distinctions really feels key to being well-informed, gives you a real grasp of what's actually happening.
It absolutely is. And if you connect this back to the bigger picture, well, this deep dive really shows how something that seems straightforward, like an explosion, actually involves complex physics, intricate chemistry, and incredibly rigorous safety protocols, all designed to manage immense power. Knowledge, as always, is the very first step in effective management and ultimately in safety.
Absolutely. Couldn't agree more. So maybe a final thought for you listening. Given what you've learned today about the specific dangers and sometimes the hidden ones, like that insidious sequence of primary and secondary dust explosions, what overlooked risks might be present in your own environment? Could be your home, your workplace, maybe even your hobbies.
Yeah.
They could benefit from a deeper look, knowing what you know now. Something to mull over.